Okay, so let's begin with today's topic. Today we'll be talking about decision trees. Now, quick recap if you remember the topics that we have covered. We started out with supervised learning first. We are yet to move into unsupervised learning. So, within supervised learning, we saw that supervised learning is of two types. One is regression and one is classification. Okay, regression is where the dependent variable is continuous in nature, and classification is where the dependent variable is categorical. Okay, within regression, we saw a few algorithms. We saw linear regression. We have covered this. Then within classification, we saw logistic regression. Okay, and now we will be starting our next supervised learning algorithm, which is decision trees. Now I have intentionally written decision trees in the middle because this can be used for both regression and classification. Okay, so this is a supervised learning algorithm that can be used for both regression problems as well as classification problems. That means you can use decision tree for problems such as prediction of the prices of houses, which is a regression problem, and you can also use decision trees for predicting if a customer will churn or not, or if a person will default on his bank loans or not. So on both kinds of problems, you can use a decision tree. Okay, is that clear, guys? Okay. And to give you another overview again of supervised learning, what is supervised learning? In supervised learning, we try to find a function like this. So this is our dependent variable, and you may have a few x's here. These are your independent variables. What our goal in supervised learning is to find this function f. Okay, this is our goal in supervised learning. We divide our data into train and test. Okay, we do a random split into train and test. We usually keep more data into train and around 20 to 30% in test. Why do we keep more in train? Because we want to use more data to build our model so that the model is robust. Okay, and then we test it on a small piece just to validate whether the model that we have built is performing good on out of sample data or not, because the training data the model would have already seen. So looking at the accuracy on the training data is not a good approach, because that the model would already have seen. So we do it on a new data set that the model has never seen before, and on that data set, if the performance is good, we conclude that the model is good. Okay, so we use the training data. In the training data, we know our y, we know our x. Okay, and by this relationship we can find the function f. Okay, this is on the training data. Then what do? We use this function f on the test data. Now f we know, and all the x's which are independent variables, we know that as well. So what we have to do, we have to find y now in the test data. In the test data we find y, and then since we already have the actual y also in the test data, we will know the actual y also. So this will be y hat or y predicted, and in the test data we already know the actual y, so we can compare whether whatever we are predicting is the same as the actual y or not. So that is where all the error parameters come. So remember, in regression we have seen the error parameters. We have seen r square, adjusted r square. We have seen the error parameters MAPE, RMSE, SSE, etc. Okay, and similarly for classification, since classification means only a 1 or a 0, so we compare using our confusion matrix. Okay, so this is how we can compare our predicted y versus the actual y. Is it clear, guys? Are all these things clear? So this has been covered already. Any questions on this? Please respond, guys. Okay, cool. Now, so far the algorithms that we have covered linear regression and logistic regression. Okay, so linear and logistic is what we have covered so far. Now, both these algorithms are parametric in nature. Okay, so what do I mean when I say both these algorithms are parametric? So parametric algorithms are those which have an underlining, which assume an underlying distribution of the data. So for example, if you remember in linear regression, I told you there are some assumptions in linear regression, right? So one of the assumptions was that dependent variables should have a linear relationship with the independent variable. Okay, so that means linear regression algorithm has a underlying assumption on the data that only if the dependent and independent variable are linear in nature, we can use linear regression. Okay. Similarly, logistic regression also has an assumption. In logistic regression, we have an assumption that the log of odds, the log of odds should have a linear relationship with the independent variable. Okay. Remember, if you remember, we got this equation. This is the equation we had gotten earlier. So what does this mean? This means that log of odds should have a linear relationship with the independent variable. Okay. So both these algorithms, they have an assumption on the underlying data that you are using. That is why they are known as parametric model. So all parametric models, they make an assumption on the underlying data. We also have another approach of solving a supervised learning problem, which is non-parametric approach. Okay. We also have non-parametric approach where we do not make any assumption. We do not make any assumption at all on the underlying data. So decision tree is one such algorithm. Okay. Decision tree is one such algorithm which does not make any assumption on the underlying data. Okay. So that means decision tree can be used no matter what kind of data you have. Whether you have linear data or data which is totally non-linear, whatever it is, you can always use decision tree algorithm. I'm not saying it will always perform better than linear or logistic, but you can use. There is no underlying assumption in case of a decision tree algorithm. So I had already shared a few reading material on this. So let me just quickly get this up here. I think I had somewhere parametric and non-parametric models. Anybody remembers in which module was this present? I did have it somewhere in the stats part. Okay. No, we don't have it here. I did have it somewhere. Was it here? No. Okay, I'll check. I'll check which part is it present, and I'll share that with you. Okay, then maybe I was waiting until now to share it. So I'll have it here. So there is some reading content on parametric versus non-parametric. I'll share it here. Don't worry. Okay. Okay, so decision tree is a non-parametric model, so there are no assumptions here. So which is good for us, so you don't have to remember any assumptions in case of decision tree. Okay, now let us look at the algorithm in details. What is decision tree and what does it do? Okay, so let me start with an example. So we will first learn decision tree for classification, and the same concept, I'll extend the same concept to a regression case also. Okay, but first let us look at a decision tree algorithm for classification. So let me start with a very simple example. Let's say I have two independent variables x1, x2 and y. Y is my dependent variable, x1 and x2 are my independent variables. Okay, so let's say we have some values here and my dependent variable is, let's say, plus and minus. Okay, I can write ones and zeros also, but instead of ones and zeros I am writing plus and minus. And let's say it looks like this. So let's say this is how my data looks like. I have plotted this data here in a graph. Okay, I have x1 and x2. I have plotted that here. This is my x1 and this is my x2. Now I want to write an algorithm which helps me predict whether it's a plus or a minus, or let's say ones and zeros. So remember, in supervised learning, what do? We try to find the function f. So in this data, we know our y, we know whether it is a plus or a minus each data point, and we know the value of x. So for each point, we know the coordinate, right? We know the coordinate of each point. So we know x, we know y. What we have to do is we have to find this function f. So help me guys, help me finding this function f. What do you think can be the function f here? What can be the function f? Okay, Bharati is saying slope of the line. Slope of which line? Which line are you talking about? I don't see any line here. Shivakumar, negative value. What negative value? I'm asking what is the function f? What can be the function f here in this data? Quickly guys, tell me. Straight line where, Anupama? Where should I draw a straight line? Yeah, of course, y will depend on dependent variables x1 and x2, Anupama. That is correct. That is true for any algorithm. Your dependent variable will always depend on the independent variable. Plus and minus is your dependent variable. But I'm asking what is the function f here? What can be the function f? How can you write a function f which will help you decide whether it is plus or minus depending on the value of x1 and x2? Bharti says a straight line passing through max number of data points. Okay, so you are saying just like a linear regression, I will draw. Let's say I draw this line. Okay, Bharti says that this line will help me. This line is the function f. Is that correct, Bharti? So how will you predict plus and minus using this line? Do you think this line will help you predict plus and minus? Remember, this is not a regression problem. How will you use this line to predict your plus and minus using x1 and x2? Do you think it is possible? Anybody? Okay, Arpita says by clusters we will identify into where y will lie. Can you elaborate what clusters do you mean? Yes, guys, can you answer? Others, Vikram, Sinoj, Pankaj, try to answer. What do you think can be the function f here? The question is, what is the function f here? What is the function f which helps you predict y using the values of x? By x I mean x1 and x2. So what can be the function f which helps you predict whether it is a plus or a minus using the values of x1 or x2? So this line will not help you, okay? Because this line, using this line, it is very difficult to find whether it's a plus or a minus. So what can be done? What we can do is, I can draw a line here. I can draw a line here and I can say whatever is on the left hand side of the line is plus, whatever is on the right hand side of the line is minus. Yes, Pankaj, you are right. Okay. So I can draw a simple line like this. I can draw a simple straight line parallel to my y-axis, and I can say whatever is on the left hand side of the line is a plus, whatever is on the right hand side of the line is a minus. So what is my function f here then? My function f will be x is equal to, let's say this point is 3.5. I can write x is equal to 3.5. So that is my function here. Or should I say x is less than equal to 3.5. Do you follow, guys? So I can write a function. This is also a function, right? This is an inequality, which also is a function. So I have written a function, a very simple function. X is less than equal to 3.5, which looks like this. If you draw it here, it looks like this. Now this will have two answers. It will either be true or it will be false for different values of x1. Let me write x1 here. For different values of x1, this will either be true or this will either be false. 3.5 here is the mid between this and this. Okay, it is the center. Yes, Sinoj. So I could have drawn a line here also. I could have drawn here also, but to be safe, I have taken the midpoint. From here to here, I have taken the midpoint here. Okay, so that I have enough gap. I have enough gap between the two. Okay, otherwise I would have enough in infinite number of lines to draw. So to avoid that confusion, I go by the middle point so that I have enough gap. Why do I need enough gap? So that it generalizes well. Okay, it generalizes well on new data point. That is why I will try to keep enough gap here. Okay, now this decision that you have taken, this function that you have taken, x1 is less than 3.5, it can either be true or it can be false. Now if this is true, what do you do? What do you get rather? You get plus. So I'll write plus here. And if this is false, you get a minus. So this is your function f, which tells that if x1 is less than this particular point, what you have is all plus. If x1 is not less than 3.5, what you have is all minus. There cannot be any other solution to this. It can either be true or it can either be false. And for both cases, you have a decision made. You have a conclusion. Either it is plus or minus. Okay. So using this decision, you will make a prediction. You will use this expression or this inequality and you will make a prediction. Do you follow, guys? Do you follow? Yes, less than 3.5 is positive. Now you understand why this algorithm is called a decision tree, right? Because you are making a decision and it looks like a tree, right? It is looking like a tree. So that is why it is called a decision tree. Okay. Now let's see another example. This was a very simple example. Let's move to a slightly complex example now. Again, the same data. I have some independent variables and I have some dependent variable. Okay. Now let's say this is how the data looks like. Now how would you find the function f? Tell me guys. How do you think you will find the function f now? Yes, here both x1 and x2 will decide because x alone, x1, either x1 or x2 alone is not enough, right? So in this case, either x1 or x2 alone is not enough to decide plus and minus. So both will together decide. So what should I write then? What should be your decision? What should I write? So let's start with the same line that I had drawn earlier, right? Let's start here. Okay. So I'll write x1 is less than equal to 4. Okay. X1 is less than equal to 4. This will have a true and a false, right? Let me write all the true here and all the false here. Okay. So if x1 is less than 4, what do we get? Do we get plus or do we get minus? We get both. We get both, right? Right? Similarly, if x1 is less than equal to 4, if it is false, that means this area. So here also we have both plus and minus. So that means we are stuck, right guys? We are stuck. So what we do is we create another split. Let's say here we create another split at x2 is less than 3.5. So what I will do is once I get x1 is less than equal to 4, which is this area, on top of this area I will draw another split which is x2 is less than equal to 3.5. Okay, x2 is less than equal to 3.5. Now this again will have true and false. So all the true is always on the left hand side as a convention. All the false is always on the right hand side as a convention. Now if x2 is less than equal to 3.5 true, what do I have? What should I write here? Yes guys, what should I write here? Yeah, it's a plus. It means this area. See, because I have already selected x1 is less than 4. So x1 is less than 4 means this area. Now inside this area I am further splitting it at 3.5. So what I get is this area only. Okay. So this decision is on top of this decision because this is inside it. It is coming from the same branch. Okay. So it is a plus. Similarly, this, it is a minus. Okay. I can do the same here. X2 is less than equal to 3.5. I can get a true and a false here. So if it is true, what do I get? What should I write here, guys? What should I write here? Yes, it should be a minus. And similarly here it should be a plus. Okay. Now I have done the same as in the previous example, but here I have a larger tree. Because one decision alone was not enough, I had to take multiple decisions. And then I got my predictions. Okay. So this is again a simple example. What you would actually do in actual examples is this would go on. This would go on for some more depth. So right now the depth is only one, but in actual data this would go on, and that is why it is called a decision tree, because you are eventually making decisions and it is looking like a tree, right? This is looking like a tree. It can go on and on like this. So that is why it is called a decision tree. Sorry, what are you asking, Anupama? It is greater than 3.5 on right hand side. Uh, which one? This one you mean? This one is greater than 3.5. Yes. So if it is greater than 3.5, it means this area. So this area is a plus. So I have written a plus here. Okay. This area is a plus, so I have written a plus here. You can have the same condition, you may not have the same condition. Okay. So in this case, the same condition was giving us the solution, but you may not have the same condition. You may have different also. Let's say if I had some minuses here, for example, then this line would move up. Okay. It depends on the data. So in this data, the same condition was enough. Okay. Any doubts on this, guys? Any doubts on this? Tell me. Think about this for a minute and tell me. I'll pause for a few seconds here. Tell me if you have any doubts. It doesn't matter. Anupama, it doesn't matter whether you write less than 3.5 or greater than 3.5. Both are correct. Okay, it doesn't matter. If I had, let's say I don't write this. I write greater than. Okay. So what would happen if I write greater than? So if I write x2 is greater than equal to 3.5, then this will become plus and this will become minus. Okay. Then this will become plus and this will become minus. They will interchange, but the conclusion wouldn't matter. Okay, so you can write that way also. It's totally up to you. You either write x2 is less than equal to 3.5 or greater than equal to 3.5. The conclusion would be the same. It wouldn't matter. Shinoj, are you asking something? Xe is less than x2 is less than equal to 3.5. Is that a question? Which both are the same condition? I didn't get the question. Can you write it in one paragraph? Arpita, yes, the line will always be parallel to the x and y axis. Okay. Yes, that is true. Because no matter what constant you write here, no matter what constant you write here, it will always be parallel. So whenever you write x1 is less than equal to or x1 is greater than equal to any constant, it will always be parallel. Similarly for x2 also. It will always be parallel to the axis. Okay, why did I get 3.5? Is because, as I said before, you will try to see the midpoint. So here, what is the positive point which is the nearest to the negative point? Similarly, what is the negative point which is nearest to the positive point? Okay, and then you see the distance between them and take the midpoint. Okay, the midpoint is coming around here. Similarly, here also, this is the positive, this is the negative. So this is the total distance between them, and you take the midpoint, which is 3.5. Okay, is that okay, Sinoj? Now you don't have to worry about this because the software will do this for you. Okay, you don't have to worry. The software will find the midpoint. You don't have to draw and find the midpoint like this. Software will do that for you. Okay. Now the first decision that you make, is known as the root node. This is just nomenclature. The first decision is the root node. Okay, because this is where the tree is. So it's like a upside down tree. Okay, it is like a upside down tree which has the root at the top, and from there all the branches start coming out. Okay, okay, and these are known as intermediate nodes. Just nomenclature. Intermediate because they are in the middle. This also is intermediate node, and these are also known as terminal nodes. Okay, all of these. Terminal because they are the end. They are like leaves of the tree. Okay, they are leaves of the tree. This is the root of the tree. Leaves is where the tree ends, right? The tree ends at the leaves. Beyond the leaves you don't have anything. So these are the leaves of the tree, and this is the root of the tree. These are intermediate nodes. Is that clear, guys? Okay, guys. So now what I would be doing is I have a video here which I'll be playing right now. Okay, which will again describe the same things that we have discussed, but in a slightly different fashion. Okay, it will describe the same things in a different fashion. So watch this video. This is a 10 minutes video. So watch this video, and then we can discuss if you have any doubts from the video. Okay. Just a minute, guys.
We have seen in a previous video that the decision tree tries to separate the two classes by taking a decision right somewhere in the middle of the two classes. So decision tree tries to split the data in such a way that the two buckets which are created are entirely consist of one of the classes. This is what the decision tree tries to. It may not be successful in all cases. Sometimes it might be impossible to separate the two classes. We have seen in a previous video that the decision tree tries to separate the two classes by taking a decision right somewhere in the middle of the two classes. So decision tree tries to split the data in such a way that the two buckets which are created are entirely consist of one of the classes. This is what the decision tree tries to. It may not be successful in all cases. Sometimes it might be impossible to separate the two classes, but that is the goal of a decision tree. To it tries as much as possible to separate the two classes, to separate the pluses from the minuses. So it takes a decision or it makes a split in such a way that pluses are separated from the minuses. Now let us understand the theory. Let us define the theory behind the decision tree and see, and then we will look at the maths that happens at the back end. So the objective of a decision tree, let us see what the objective of a decision tree is. The objective is to create splits on independent variables. Remember, we were splitting the independent variable, not the dependent variable. Okay, so the splits were being made in the independent variable space. So in the previous example, we split it on x1 and x2, not on y is our plus and minus. Y, the separation of plus and minus is the result of the split, but the splits are actually being made on the independent variables. So create splits on independent variables to form pure or homogeneous buckets. What do I mean by pure or homogeneous buckets? So buckets which entirely consist of either pluses or minus. So this is what the decision tree tries to, but it may not be successful all the time, but that is the goal, so that it can form pure or homogeneous buckets. Or I can say buckets which have more of one class. So more of ones or more of zeros. So even a situation where you have, let's say we have a situation where we have two pluses and two minuses in the same bucket. Now this is the worst form of impurity. This is an impure bucket. Why impure bucket? Because both are equal in numbers. So it is 50-50. This is the worst form of impurity. So what is, even if I am able to make it like this, let's say 1 plus and 2 minus, this is better. This is still pure compared to that because I have two minuses here. I have two minus, so I have more of one class and less of the other class. Similarly, even if I am able to form 2 plus and 1 minus, this is better than this one. So this is worst. This is better, and even this is better compared to the first one. 2 and 3 are better because they have more of one of the labels. This has equal number of both labels. This is the worst form of impurity. Of course, if you can get to this level, number 4, this is the best. So this has zero impurity. Why zero impurity? Because both are pluses. There is no impurity here. It is entirely made of pluses. So that is the goal of a decision tree, to ultimately reach to this stage. Sometimes it may not be able to reach to this stage, but at least it will come till this stage. So it will move out of this worst form of impurity. So that is the goal of a decision tree. And where are the splits made? We have seen the splits are made at the midpoints of consecutive pair values of independent variables. So I intentionally splitted this at 2.5 because it was midpoint of 2 and 3. Otherwise, we can draw infinite number of lines between 2 and 3. So there would be a confusion that which line to select, because there can be infinite number of lines and all of these lines will be able to perfectly split the pluses from the minuses. So which line do we select? We select the line which passes right through the middle of the consecutive points. Now the question is, how do we measure impurity? So we were talking about creating pure buckets or uniform buckets or homogeneous buckets. How do we create them? Now, a computer will not draw plots like this. So this is for human understanding that I have drawn this. A computer will not draw plot like this and then decide where to split. Or imagine if you have 10 independent variables, then your data would be into 10 dimensions. Coming up with a plot and then figuring out where to split would be almost next to impossible. So how do we do that in that case, or how does a computer do that? So that is where we go to the underlying maths of a decision tree. We have a variable, a parameter called Gini index. So Gini index is a mathematical parameter which measures the impurity in a bucket. So Gini index is a mathematical parameter which measures the impurity in a bucket. Remember, it measures the impurity. And what is the goal of a decision tree? The goal of a decision tree is to form pure buckets. So the goal would be to minimize the impurity, to minimize Gini index. The goal of a decision tree would be, let me write it down here, it would be to minimize this quantity. It would be to minimize the value of Gini index, and as it minimizes the value of Gini index, it indirectly increases the purity of the bucket, which is the goal of a decision tree. Now, how is Gini index measured? It is a mathematical quantity which is measured by this formula, 1 minus summation of pk whole square. Now, what is pk? Pk is the proportion of each class in each bucket. We will see this with an example in details, but this is the formula. It is a proportion of each class. So if you have a binomial class, it is a proportion of zeros and the proportion of ones in each of the buckets. If you are splitting into two buckets, you will calculate the proportion of 0 in bucket 1 and proportion of 1 in bucket 1, and then similarly you will calculate the proportion of 0 in bucket 2 and 1 in bucket 2. And m represents the number of classes you have. So we usually deal with a binomial classification problem. In that case, m will be equal to 2 in case of a binomial classification. Now let us see this with an example. Let us see how do we calculate Gini index and how does it help a decision tree come up with the appropriate split with an example. So let me take a very small data. I'm taking a small data because it involves manual calculation. The computer does this for us, so we don't need to do this. But to understand the maths, this is important. So let's say this is our data. I have two variables, x1 and x2, and so where would we split here? We have already seen this example. We would probably split at somewhere here. Somewhere here we would split, and this would give us pure buckets, exactly pure buckets. Now, why did we split here? Because the Gini index, as a result of this split, we will see now that it turns out to be the least. And remember, that is the goal of a decision tree, to minimize the value of Gini index. So let me write down the goal. The goal is to minimize the value of Gini index. And we will see now that once I split here, the Gini index will become the minimum. Now let's say somebody else does not agree to this and he says that no, I will make a split, let's say here. He's adamant on making a split here. He makes a split here. So I will calculate the Gini index for both green split and the red split, and we will see which gives us the lesser value of Gini index. And whichever split out of green and red, whichever gives us the least value of Gini index, we will be selecting that split. So let's calculate. Now, before we in fact go ahead with a split, let us calculate the Gini index present in our data entirely before we split. So what we try to do using a decision tree is we try to reduce the value of Gini index, or we try to reduce the impurity. So first we will have to calculate what is the impurity that we are starting with so that we can reduce it further. So let me write it down here. I'll write before split. So let me use the same formula, 1 minus summation of pk whole square. And before split, I do not have any split, so this all the points are in one bucket. The entire data is in one bucket. So how will I do this? 1 minus, this is the proportion. So proportion of plus, let me write the proportion of plus whole square, and then since I have a summation sign, I will write proportion of minus whole square. So let us calculate this. 1 minus proportion of plus whole square. What is the proportion of plus? I have 1, 2, 3, 4, 5 points in plus, and total I have 5 points in minus also. So the total becomes 10. This is the proportion, remember. So it is 5 by 10 whole square. And once again, I have 5 by 10 whole square because I have 5 plus points and 5 minus points. So this gives me, so 5 by 10 into 2. So this will give me 2 into 1 by 4. So this will cancel out and it will give me 1 by 2. So 1 by 4 plus 1 by 4 will give me 1 by 2. So it gives me 1 by 2. So I get 0.5 as the answer. So this is my Gini index before split. Now remember, I briefly talked earlier that this is the worst form of impurity you can get, where you have equal number of pluses and minuses in the same bucket. Remember, before split, everything belongs to the same bucket. I have equal number of pluses and minuses in the same bucket. This is the worst form of impurity, and the worst form of impurity is giving us a Gini index of 0.5. So what does this tells us? This tells us that the worst value of Gini index or the maximum value of Gini index is 0.5. Gini index cannot go beyond 0.5. This is the worst form of impurity. Now let us go ahead with the split. Now after split, now let us see which split is better. First I will calculate the Gini index for the red split. So let me calculate for red split first. So the red split happens here. I have two buckets now. In the red split, I have, let me call this bucket 1 and this bucket 2. So first I'll calculate the Gini index for bucket 1. So bucket 1, what is the Gini index? It is 1 minus. Now proportion of plus in bucket 1, how many pluses do I have? 1, 2, 3, 4. I have 4 plus in bucket 1, and total how much do I have? I have 5. So 4 by 5 whole square plus I have 1 minus, so 1 by 5 whole square. So this is the value of Gini index. Let me directly take it. 4 4 is 16 and 1 17. So this is, let me calculate this quickly with a calculator. So 25 minus 17 by 25, it gives me 0.32. So this is the value of Gini index in bucket 1, 0.32. Similarly, I will calculate the Gini index in bucket 2. So let me quickly do this. I have 1 plus and 1, 2, 3, 4 minus. So this is similar. I'll get similar answer because this will come here and this will go there. The proportions interchange here. So I think I'll get the same answer here as 0.32. So this is the Gini index in bucket 1 after the red split, and this is the Gini index in bucket 2 after the red split. So the total Gini index after split, total Gini index after the red split, now how do we calculate the total? We don't just add them up, we take a weighted average. So weighted average, weighted by the number of points they have. So the number of, let me write the formula for that. The number of points in bucket 1 into Gini index of bucket 1 plus number of points in bucket 2 into Gini index of bucket 2, and all of this divided by total number of points, so n total. This will be the Gini index after split. Okay, so let's calculate this. What is the number of points in bucket 1? I have 5 points, so 5 into 0.32, and here as well I have 5 points, so again 0.32 into 5 divided by total 10 points I have. So how much would this give me? So 5 plus 5, so it would give me the same answer as both has equal number of points. So I would get a Gini index of 0.32 after the red split. So see, the Gini index reduces. Initially, we started with a Gini index of zero point 0.5, and even the red split gives us reduces the Gini index. So it does reduce impurity to some extent. It reduces it to 0.32. But remember, we will select that split which gives us the least value of Gini index. So let us see what Gini index do we get after doing the green split. So now let's calculate the Gini index with green split. So again, even when we do a green split, we divide the points into two buckets. So this is my bucket 1 and bucket 2. Let's calculate the Gini index for the first bucket. So we can see the first bucket has only minuses. I have 5 minus points. So let me calculate for bucket 1. I have 5 minus points here. So remember, I'll write the proportion of minus 5 minus points divided by total. I don't have any plus, so it is 5. And I have 0 plus points, and total is also 5. So I'll do this. This is the Gini index in bucket 1 after the green split. So 1 minus 1, it gives me 0. So the Gini index is 0 in bucket 1. Similarly, if you calculate for bucket 2, again bucket 2 has only plus points. So again this will interchange and I will get another 0. So the weighted average of 0 and 0 is again 0. So Gini index after the green split is 0. Now what do we see? We see that we started with a Gini index of 0.5 and the red split gave us a Gini index of 0.32, which is less but not the least, and the green split gave us a Gini index of 0, exactly 0. So this means that the green and Gini index cannot go below this. This is the purest form. You can see it is the purest form. We have entirely split our labels into pluses and minus. So this is as pure as it can be, and the Gini index for that is 0. So this tells us that the green split is better than any other split. So we tried with one. You can try with any other split in this case. None of the splits will be as good as the green split. So the green split is the best one, and hence the decision tree will select the green split. So this is what the algorithm does. Once you run the algorithm using codes, which we will see in a later video, the algorithm will try all possible splits and finally select the one which gives the least value of Gini index. In some cases it may not be able to arrive at the final Gini index of 0, but the Gini index, whatever it arrives at, will definitely be lesser than what it started with. So the Gini index after split will definitely be lesser than the Gini index before split.
Can you hear me, guys? Okay. So was that clear, guys? Did you understand? Did you understand how mathematically we can take care of this? So until now, whatever we had been doing was through visualization, right? So what we were doing is we were drawing x1 on y-axis and x2 on the other axis, and then visually we were looking where is all our minus and where is all our plus, and based on that visually we were trying to create a split. Okay, but not always you will be in a situation to do this because your data might be in multiple dimensions. Let's say you have 10 independent variables. Then how would you do that? You cannot plot 10 independent variables on your screen and decide it. So it becomes very complex as you move to a higher dimension. So that means there must be a mathematical way of doing it, and that is what we discussed just now. What is the mathematical way of making a split? So always remember, quick recap of what we saw in the video. We saw that the mathematical way of doing this is minimizing the value of Gini index. Okay, what is Gini index? It is the impurity in a bucket. It is the impurity, and the goal of decision tree algorithm is to minimize the impurity or minimize the Gini index, okay, or to form pure buckets. So any of these is the goal of a decision tree algorithm. It tries to create splits in the data so that after the split we have more pluses or more minuses together. We do not have a mixture, we have either pluses or minuses. Sometimes it may not be possible to get exactly pluses and exactly minuses, but then it will try to have at least more pluses than minuses. So let's say if there are 10 pluses and only one minus, only one minus. This is of course better than 5 plus and let's say 3 minus. This is in a better situation. So from this kind of a situation, it will move to that kind. Okay. So that is the goal of a decision tree algorithm. It will try to minimize the value of Gini index. Okay. So that is how mathematically the software does. The formula for Gini index is this. Okay. Where Pk is the proportion of all the classes. So proportion of plus, or I can write it like this: proportion of plus whole square plus proportion of minus whole square. Okay. This is the formula for Gini index. Okay. So you will try to minimize the value of Gini index as it measures impurity. It is measuring impurity. So you will try to go to a lower value of Gini index after split. So that's what we saw in the example. We took two splits and then we saw that the green split was giving us a better value of Gini index or a smaller value of Gini index. Hence we go ahead with the green split and not the red split. Okay. Any doubts, guys? Any doubts so far? Bharti, you were asking something, right? I didn't get your question. What is 4 by 10? Okay. Yes. Yes, because there were 5 plus points and 5 minus points also. So the proportion is 5 by 10 of both pluses and minus. Right? Did I miss anything there? Later for red split, I took 4 by 5. Oh, is it? Okay, one second. Let me get that up again. Here? Is it here, Bharti? Why 4 by 10? For the red split, because when I'm, see, it is, okay, one second. Yeah, the red split, right? Because I'm only calculating in bucket 1. So I'm only using the points which are in bucket 1, not all the points. This is before split. Okay, this is before split, which means I'll consider all the points. So this portion is before split. Look at this, it is before split. That means all the points I will consider. But this is after split. Look at this heading, this is after split. So that means only B1. Here I am considering only B1. That means only these points. I have only 5 points in B1. Then once again I will calculate for B2. Then I will consider only points which are in B2. See, I have done B1 and B2 separately, which is why I took 5 and not 10. This is before split. Before split, everything is the same. Both the buckets are the same. Okay? Okay, cool. Any other doubts, guys? This is a very important concept and this is asked a lot in interviews, and most people don't know this. Running just a decision tree is very simple. You just have to run 2 3 lines of code, but understanding the maths behind is the important part, which most people lack. Sorry, yeah, I had gone on mute. So let's say these are the three classes we have. We have plus, minus, and these stars also. Okay. So our decisions will look something like this. If x1 is less than 5, true, and this side is false. What do I have? If x1 is less than 5, I have plus, right? If x1 is not less than 5, I have both of these. So I will go for a further split. x1 is less than 10. Then again true and false. Now if it is true, I will have minus. If it is false, I will have star. So this way you can go. Do you follow? Do you follow this example for a multiple class problem? So this is how you will proceed in such cases. But always remember, the number of branches coming out of a node will always be 2. It cannot have more than 2 branches, because you can either be true or false for this. You cannot have any third thing. Okay. And also remember that in a node you will always have only one variable. You cannot have something like this: x1 is less than equal to 5 and x1 is less than equal to 10. You will never have this. It will only be either this or this, only one variable at a time. Not a and or a if condition will not be there. Okay, so remember that. Any other doubts, guys? Okay, if you have many independent variables, then you will select the best independent variables. What do I mean when I say best independent variables? You will select those independent variables which help you reduce the value of Gini index. So the software will do all the calculations, and it will automatically find out which is the independent variable which is giving me the least value of Gini index, and accordingly it will do. Okay, so that's the advantage of using a software. You wouldn't have to do this for all the independent variables. The software would do that for you. It will automatically decide which is the best independent variables and where to split in that independent variable. Okay. That's what I'm telling, Anupama. Why two? You can have more than two independent variables. Why just two? So I can have a tree which looks like this. X1 is less than 5. It goes like this. Then I will have x2 is less than equal to 3. Here I can have x5 is less than equal to 9. and this goes on. X11 is less than 2, X15 is greater than equal to 10, and on and on. I can have like this. I can have more than two independent variables in my overall tree. I have X1, I have X2, I have X5, I have X15, X1 again. So anything is possible depending on which variable is giving the least value of Gini index. Remember the goal. The goal is to minimize Gini index. Whichever variable, whichever independent variable helps me do this, the software will automatically select that. Okay, no matter how many you have. Okay, so in the LMS, I will have a few assignments on this. So for example, you will have a quiz which will ask you exactly to do this. So in this quiz, I'll have a CSV file shared to you. And if you see the questions are such, you will have to calculate the Gini index before splits are made and after making some splits. So do this using your pen and paper, not using the software. Okay. So do this. So all questions has to be answered using a pen and paper only. So attempt these questions and you will have all the doubts resolved. That's what, Arpita, again the same question. Which split to consider first in case of multiple independent variables? That split which gives the least value of Gini index. It will do a priority. Whichever split gives the least value of Gini index, and that will always be one split. So it will select that independent variable or that split which gives the least value of Gini index. Okay. So let's take a break, guys. Let's take a break at this point, and after the break, we will discuss the concept of overfitting and underfitting. Okay. So it's 10 o'clock now. Let's be back by 10:15. Okay. So the next topic that we will be talking about is overfitting. Okay. So overfitting is not an algorithm. It is a concept which applies to every algorithm. Okay. So let me explain you overfitting with an example. Let's say I have my dependent variable y and I have my independent variable x. I have just one independent variable, and let's say these are the points. Okay, these are the points that I have, and I'll be drawing two algorithms. I'll be drawing the graph of two algorithms. This is, let's say, algo 1 and this is algorithm 2. So algo 1 is this green one, algo 2 is this pink one, let's say. Okay, so that's the graph of algo 2. Let me draw the graph of algo 1. Let me draw one more, algo 3. Which is this. This is my algo 3. Okay, now look at the three colors. Okay, guys, look at the three colors, the pink one, the green one, and the gray one. Okay, each of these represent the function according to algorithm 1, 2, and 3. Okay, and the points that you see on the graph are the points that you have to predict. So these are the points that you have to predict. So these are your y. Now, which of the three algorithms do you think is the best and why? So think about this, guys. Think about what you have understood so far. What is the goal of any algorithm? Okay. So remember, any algorithm, we try to predict y given the values of x. So which of the three algorithms do you think is better than the other and why? Anupama says algorithm 2 is better. Okay. What about the others? Why not algo 1 or algo 3? But Anupama, the pink one passes through. Okay, yeah, that's why you have said pink one. Okay. Okay, Bharti also says Algo 2 is better fit with the data points. Okay. Anybody who has a different answer, who thinks Algo 2 is not the best? Anybody? Okay. Algo 2 since error is minimum. Okay. Fair point. Anybody who thinks Algo 2 is not the best one? Okay. So what about the others? Amit, Pankaj, Sinoj, Vikram. What do you guys think? Which one is the best? Okay. The answer is Algo 2 is not the best. Okay. Okay, so all of you think the pink one is the best, but the pink one is not the best. Vikram says Algo 3. No. Actually, Algo 1 is the best. Okay. So good. This is what I expected from you. I expected most of you will say the pink one, which is fair because based on whatever has been covered so far, you would probably think that the pink one is fair. Okay. So no problem with that. Now let us understand why the pink one is not the best. The if you look at the error, definitely the pink one has the smallest error because you can see that the pink curve almost always passes through the points. So if you find the errors, it will have the smallest error. Okay, even smaller than the green one or the gray one. But still, I'm saying the pink one is not the best. Why? That is because this will not generalize well on new data points. So remember, this is the training data that I'm showing you. Whatever points that you see here, it is the training data. This is not your test data. Your test data might be something else, might be different. So your test data may be, let's say, these are your test data. Let's say these are your test data. The blue ones are your test data. Okay, the blue ones are your test data. And always remember, how do we evaluate a model? We evaluate a model based on how it performs on the test data, not on the training data. So on the training data, definitely the pink one performs the best. But does it perform the best on the test data also? That is something which we'll have to see. Okay, but looks like it will not perform good on the test data because it is too complex. It just tries to memorize the type of pattern you have in the training data, but in the test data you might have a slightly different pattern. Okay, so it is too complex. The pink one is too complex. Okay, it is too complex, and so probably it will not generalize well on new data points. Okay, because it is so complex. So you can see it has gone and it has taken these kind of curves. Okay, and these curves are not at all touching the test data points. It might touch a few, but more or less they are not touching the blue points, which are the test data points. But on the other hand, if you see the green one, the green one is pretty close to the test data points also. Okay, so I would say that the green one is the first best, this is probably the second best, and this is the third. This is the order. Okay, this is best, this is worst. Okay, because it is too complex. The pink one is too complex. It is so complex that it will not generalize well on new data points, or it will not generalize well on the test data. And on the test data is where we measure the accuracy of a model, not on the training data. Okay, so it is too complex. That is what is overfitting. Overfitting means it has memorized the data. It has memorized the data more than it should have. It has memorized the noise present in the data. Okay, so every data has pattern and it has noise. Noise means something which happens randomly. Okay, so when your model is overfit, it means that your model has taken the noise as a pattern. Okay, your model has taken the noise and thought it to be a pattern, but actually that is not a pattern. So it has become overly complex. No, nothing to do with normal distribution, Hima. This is not a normal distribution, this is just a curve I am drawing. Let me give you an example, okay, of overfitting. So let's say this is your office. Why is the second one better? Because the third one is too simple. Okay, the third one is too simple. It is an underfit model. So if you look at the third one closely, this is the baseline model. Do you remember the baseline model, guys? What is the baseline model? The third is the baseline model, this one. So no matter what value of x no matter what the value of y is, or what value of x is, it always predicts the same y. So this y, the prediction of the third model does not change with respect to x. It remains the same. So for whatever value of x you see, it is always having the same prediction. So it is a baseline model. So it is too simple. It is too simple, which is also not good. Okay, so there is a trade-off. You cannot go to a very complex model. You cannot go to a very simple model also. You have to be somewhere in the middle. Okay, that is why the third one is the worst, because it is too simple. It doesn't change at all. Given the values of x, it doesn't change at all. It is a constant, basically. It is a constant, like the baseline model. A baseline model, if you remember, always predicts the average irrespective of the value of independent variables. So in a baseline model, you don't even look at this. You just write y is equal to y bar, which is the average. So there is no x here. You don't consider the x at all, which is too simple. Okay. So yeah, I was giving you an example of overfitting. Let's say this is your home. Okay. This is your home, and let's say this is your office. Okay, this is your office. And this is the path you take from home to office. Okay. Now let's say on a certain day, let's say on a Wednesday, you were going to office and there was a heavy rain. And because of that, there was some water logging in this area. Okay. So you did not go via the straight road. What you did is you took a alternate path like this. You went from here to here and then you took a left and then you came via this and went to office. Okay. This is what you did on a Wednesday because it was raining and there was some water logging here. Okay. Now if you have a overfit model, if you have a overfit model, what it will do is it will predict that every Wednesday you should take this path. Okay, because it has memorized the data. It has overly complicated the pattern. See, it rained on a Wednesday. That is why you took this path, not because it was a Wednesday. But a overly complex model will memorize that, okay, it is a Wednesday and you are taking this path. So that means every Wednesday you will take this path, which is wrong. It was not due to the day of the week, it was due to the rain that happened. But a model will, so this is a noise. Wednesday taking a path is a noise in your data. This is not a pattern. So you will not want your model to catch this. But a overly complex model will catch this information also, which is wrong. Okay. So that is why we try to avoid being taking the model to a higher complexity, or making the model too complex, to avoid allowing the model to consider a noise as a pattern. Okay. And an underfit model in this case will be that every day take this path. That is also wrong, because if it rains I should take this path. But a underfit model or a very simple model will always say that this is the shortest path, so always take this irrespective of rain or traffic or whatever. Okay, so that is a simple model. So what your ideal model in this case will be, that if it rains take this path, otherwise take this path. That is a ideal model. So neither overfitting nor underfitting is good for your model. You should be somewhere in the middle. Is that clear, guys? Do you understand this concept? Yes. So how do you detect noise? I will tell you how do you detect overfitting in your data. By that you will be able to identify what is noise. A noise is something which is not a pattern. Okay. A noise is something which is not a pattern, which is randomness in your data. So for example, rain on a Wednesday was a randomness. Rain on a Wednesday was not a pattern. Rain was a pattern, and but rain on a Wednesday was a randomness. It is out of randomness that it rained on a Wednesday. It will not repeat in the future. Every Wednesday it will not rain. It was just a random thing which happened. So this is something which you want your model to avoid. So let's see, how do we identify overfitting? Okay, how do we identify overfitting? So we have our training data, we have our test data. Let's say your model gives 90% R square on training data, and it gives, let's say, 60% R square on test data. Is this good or is this bad? Yes, guys. So this is exactly what we were discussing here. The pink one. See, look at the pink one. The pink one has very high accuracy on the training data, but on the test data, which is the blue point, it does not have a good accuracy. So this is exactly what a overfit model gives you. So this is where you have overfitting. Okay, this is overfitting, where you have very good accuracy on the training data but very poor accuracy on the test data. This is overfitting. So this is where you can identify overfitting. If your model gives you very high accuracy on training data but comparably low accuracy on test data, that is where overfitting happens. Okay. Similarly, if you have, let's say, 50% here and let's say 50% here also, what does this mean? This is not overfitting. This is not overfitting. But does this mean this is this underfitting? Yes, guys, is this underfitting? Not sure. Maybe this may be underfitting. We are not sure. We cannot say. Maybe it's the best you can do. It may be underfit also. So let's say now you have 60% here and 65% here, or let's say 63% here. This is probably good. This is good. because you have comparable accuracies on both training and test. Okay, you should have comparable accuracy, not such a big difference. This is a big difference. This delta should not be high. Plus minus 5% is okay. Okay, because you have different data in test and train, so obviously you will not get the exact number. If you have 90% in train, you will not get exact 90% in test. Plus minus 5% is okay. Plus minus 5% is okay, but the difference should not be 90 and 60. It should not be like this. This means that you are overfitting. Okay, this means you are overfitting. So this is how you can identify overfitting in your data. If your model performs very well on the training data but not so well on the test data. Okay, by not so well I mean you cannot say if it is 90% in training and if it is 88 in test it is overfitting. No, it should be more than, the difference should be more than 5%. Only then you can say that it has overfit. Plus minus 5% is random variation that can happen anytime. Okay, but it should not be more than 6%, let's say. So if it is 90% in training and if it is 82% in test, then probably you have overfit. Okay, but if it is 90 and 87, that is okay, that is random variation. Are you following, guys? Why not 50% is best? So Anupama, what kind of let's say you are giving an exam, is 50% marks, is securing 50% marks in the exam better, or is securing 60% marks is better? Of course, 60%, scoring 60% is better than scoring 50%, right? So for the same reason. So this is better, right? Here we are doing better than here. So this is better. Okay. When you take second row alone, see this row means that it is not overfitting. That's all you can say. This means that it is not overfitting. But you cannot say that this is not underfitting. When you have underfitting in both training and test, you will have low accuracy. So it is very difficult to identify underfitting. Okay. So overfitting you can identify. So let me write like this: train, test in high and this is low. Okay. Okay. So this is how you can identify. Now it should be clear. Okay. That will never happen, Bharti. So that is equivalent to saying that you haven't prepared anything for an exam and yet you scored 100% in the exam. That never happens, right? That will only happen if there has been some kind of cheating. For example, the paper was leaked and you got to know the questions in advance. Or in other ways, your training test split was not done properly. In those cases, it can happen. When your train test split was not done properly, then it can happen. But in all other cases, that will never happen. You can never build a model and on the training data it performs poor and on the test data suddenly it performs very well. That never happens. Again, plus minus 5% is okay. That is out of randomness, but not more than that. That will not happen. Okay. Now let us see. Now we have seen what is overfitting. Okay. Now let us see overfitting with respect to decision trees. Okay. We will see overfitting with respect to decision trees now. Let's say, I have this data. Okay. I have this data x1 and x2 and these are my y. Now if I go on splitting here, I'll create my first split here, right? Then I can say that this is a minus and this is a plus, right? But I see two pluses here. So what I will do, I'll create further splits which will look something like this, right guys? I will create splits like this. I'll create small buckets like this, right? Are you following? I'll create small buckets like this based on x1 and x2 and I will separate this entire space, right? Now is this good or is this bad? Creating these small buckets, is that good or is this bad, and why? Yes, exactly. Okay, so this is the reason why it is bad, for the same reason that we discussed here. So this is another way of being having a complex model. Since decision tree creates buckets, if you create too many buckets and very small buckets, that is also bad. That is also making your model very complex. So this will not result in a good accuracy on the test data. On the training data, it will be good, but on the test data, it will not be good. So that is why this is bad. Okay. So that means if I have to write this as a graph, let's say this is number of splits, okay, and this is your accuracy of tree. How do you think this will look like? Let's say for the training data. For the training data, how do you think it will look like? Tell me, guys. As the number of splits increases, the accuracy, will it increase or will it decrease? For the training data, let's do for the training data first. Will it increase or will it decrease? Yes, that is correct. It will increase. It will go on increasing. As we discussed, so for example, this pink algorithm, it will always have very good accuracy on the training data, right? We are talking about the training data, it will have good accuracy. So the more complex you become, the better it is on the training data. So it always increases like this. Now, what about the test data? Yes, guys, what about the test data? Will it increase or will it decrease? Yes, anybody? So what if the number of splits is very small? What if the number of split is very small? Let's say zero split. If the number of splits is zero, what would happen? Will it be good or will it be bad? If the number of splits is zero, will it give you good accuracy or bad accuracy on the test data? Bad accuracy, right? Because you haven't made any splits. So it is like the baseline model, right? Remember logistic regression, what was the baseline model? The baseline model is which predicts the mode. So without any splits you will predict the mode, and predicting the mode is not a good idea. That is a very simple model, right? So it will be bad. As you increase the number of splits, the accuracy will increase. The accuracy will go on increasing, but after some point the model will start becoming complex. This is where the model starts to overfit, and then the accuracy will start falling. So this is how it will look like for the test data. Okay, the model's accuracy will increase up to a point. After that, overfitting will start to happen. Okay, and the accuracy will start to decrease. So beyond this, if you increase the number of splits, the accuracy will fall. So this is where overfitting happens. Okay, towards this side overfitting happens, and this is where you have underfitting. Okay, underfit means very simple model. Very simple model means a model with very few splits or zero splits. Okay, so there is a trade-off. So you try to be somewhere in the middle here. This is the best area to be. Okay, do you understand, guys? Now relate this with what I had written here. So overfitting, training is high and test is low. So look at this here. In overfitting, training is high. So the green one is high and the blue one is low. That is overfitting, right? And then in underfitting, both are low. So look here, in underfitting, both are low. Okay. And ideal model is where both are good, right? So ideal model is here in the middle where both are good. Okay. Do you follow, guys? Guys, any questions? Okay, so we have seen what is overfitting and what is underfitting. Now, similar to overfitting and underfitting is a concept of another concept of bias versus variance. Okay, we have another concept of bias versus variance. So, bias is when you either over predict or under predict. So what is over predicting? When you predict more than the actual value. So let's say actual value is 10 and you always predict 15, or actual value is 20, you predict 30. So you are over predicting or you are under predicting. So let's say you are predicting 7 and here 15. So a model which always either over predicts or under predicts is a biased model. Okay. So it never gets the predictions correct. It always either over predicts or under predicts. Now, what is a variance, high variance model? Variance is something which how wide is your output, or how much varying is your output. That is the variance. Okay. So for example, this is best understood with a bullseye. So let's say this is a bullseye. So this is your actual value, the target. Now, what will be a high variance model? A high bias model, sorry. A high bias model will be a model which predicts totally away from the target. This is a biased model. Okay, it is predicting away from the target. Now, what is a high variance model? A high variance model, on the other hand, will be a model which predicts all over the place. So look at this model. It predicts all over the place. There is high variance in the output. Sometimes it predicts here, sometimes here, sometimes here, sometimes here. So it predicts all over the place. That is a high variance model. Okay. Do you follow, guys? So let me show you this graph and then it will be clear. So look at this graph and you will understand bias and variance. Okay. So you have two axes here. This axis is your bias axis. Okay. And this is your variance axis. So this one is low bias and low variance. So you see, it is not very far away from the target. It is not very far away from the targets. Sorry, this is high bias. Okay, so it starts from here. 1 second. Yeah, it starts from here. This is your variance and this is your bias. Okay, so this is low bias because your prediction is almost on the target, so you are neither over predicting nor under predicting, so you are exactly on the target, so it is low bias. Similarly, this one is high bias because you are away from the target. You are away from the target, so it is high bias. Similarly, let's look at the variance axis. Here your output is not scattered. Your output is not scattered a lot, so it is low variance. Here your output is scattered a lot, so it is high variance. And this is both high bias and high variance. Your output is scattered plus your you're not predicting on the target, so it is high bias. This is high bias, high variance. Okay, this is high bias but low variance. This is high bias but low variance. Sorry, I wrote the opposite. This is low bias but this is low bias but high variance. This is high bias, high variance. This is low bias, low variance. This is high bias, low variance. Do you follow, guys? Do you follow this? Okay, so usually what is seen is, as your model becomes overfit, as your model becomes overfit, you move towards high bias. Okay, because your output starts to get scattered. So overfitting means high bias. Always remember, overfitting means high bias, and underfitting means high. Sorry, I said the opposite again. Sorry about that. So overfitting means high variance. Okay, overfitting means high variance, and underfitting means high bias. Okay, so let me write this on the note. So overfitting is high variance, okay, and underfitting is high bias, okay. Because when your model is underfit, so logically if you see, it makes sense intuitively also, because if your model is underfit, means it is a very simple model. In that case, obviously you will not predict well. You will either over predict or you will under predict. So that is why it is a high biased model. Okay, and variance, when you overfit, when you memorize the data, your predictions change a lot, so it becomes a high variance model. And similarly, underfit means your model is too simple. If your model is too simple, you cannot expect it to hit the target, so it will have high bias. Okay, so all of this is discussed in details, so again from scratch, though I have covered this in the class, but all these topics are discussed from scratch in these videos. Okay, so overfitting, underfitting, everything is discussed from scratch in these videos. So guys, do watch these videos, and let me know if you have any doubts. Use the discussion forum. Okay, use the discussion forum. I will share more reading materials. If these videos alone do not help you, just ask a question in discussion forum. What doubts do you have? And I will reply. I have a lot of other reading material which I have uh, taken from the internet. So there's a lot of reading material. So what is overfitting, what is underfitting, with graphs it is shown, how to prevent overfitting, all of this is covered. Okay, so read these guys. So this is what we saw, right? We saw this graph already. We saw it with respect to accuracy. Here I have shown with respect to error. Okay, and this graph we have already seen. So do notice, do observe, do watch these videos. Okay, so these two modules are very important: overfitting, underfitting, and your decision trees. Okay, so tomorrow we will see how to run decision trees in Python. So we have seen the concept and the maths today. Tomorrow we will see the how to run these in Python. So any doubts guys from today's class? This is all I have for today. I'm still not feeling very well. Otherwise I would have taken maybe half an hour more. But I think we have covered a lot of important concepts and slightly difficult concepts today. So I should keep the class short. So let's do a quick revision of what we saw today and then conclude. So we started with first decision trees. We saw that decision tree is another supervised algorithm which can be used for both regression and classification. Pankaj, that will be tomorrow's topic. So tomorrow we will see that in Python. We are yet to see how do we control for overfitting in case of a decision tree. That is where we will see that topic. Okay. So we saw that decision tree can be used for both regression and classification. And then we saw what is the goal of a decision tree. The goal is to form uniform buckets. The goal of a decision tree algorithm is to form uniform buckets. So this is the goal in English. In maths, if I have to write, the goal is to minimize Gini index. Okay, Gini index is 1 minus summation of pk whole square. This is the Gini index, and that is the goal of a decision tree algorithm, that it has to minimize the value of Gini index. Okay, we saw with several examples how the Gini index reduces as we go on splitting. Okay, and the decision tree automatically selects which independent variables to consider for splitting. Let's say if you have 10 independent variables, the decision tree will automatically find the best independent variables to be considered for split. Okay, and where it has to split also, the decision tree algorithm will find out where it has to split with respect to any particular independent variable to get the least value of Gini index. Okay, we saw how a typical decision tree looks like. We have true on the left hand side, we have false on the right hand side. We start with a root node, then we get some intermediate nodes, and the tree grows on like this. Okay, we have a tree which grows on, and at the end you have the leaf of the tree, or you have the terminal nodes. These are the terminal nodes or the leaves of the tree. In the middle you have the intermediate nodes. Okay, then we saw a very important concept of overfitting, right? So overfitting is your when you have a overly complex model which performs good on train but not on test. Okay, that's a overfit model. And similarly, underfit model is a too simple model. A very simple model is a underfit model. It neither performs good on training or on test. Then we saw bias. What is bias? When you are away from the target. Okay, when you're not predicting well, that is a biased model. Underfit models are biased models. Okay, and then you have variance. It means when your when your output is scattered a lot. When your predictions are scattered a lot, that's a high variance model. That happens when your model is overfit. Okay, when your model is overfit, your output gets scattered. So these are very important concepts that we have covered. So guys, I want you to revise all of this before tomorrow's class. So go to the LMS. I will share today's recordings also on the LMS. I'll put it here. I'll put it here in this section. So revise all the stuff that we have covered today. Watch the additional videos that I have shared here, and then tomorrow you will be in a better situation to understand what we'll be covering tomorrow. Okay.